We will begin Unit 2 by looking at factoring. Now, before we actually try to factor something, let's talk about what a factor is. A factor, as a noun, is what we call numbers or values that are multiplied together. Factoring is a verb, and it means that we're going to take an expression and rewrite that whole expression in terms of multiplied factors. So if you look at this first expression I have here, I have two terms and they're added together. Now within the terms I do have factors because this 9, the a to the third power, and the b to the fourth power are multiplied together. So each one of these is considered a factor. But I have this overarching addition here. So I'm adding two different terms that have multiplication inside the terms. What I want to do is I want to pull out factors to rewrite this entire expression in terms of factors that are factors of the entire expression. To do this, I want to look at each term and I want to look for common factors between the terms. So I want to look for factors that are present in both terms in my expression. So for instance, let's look at the constants, these coefficients out front. I have a 9 here and I have an 18 here. 9 and 18 have a common factor because 18 is divisible by 9. So 9 goes into itself, 9 is a factor of itself, and 9 goes into 18, so 9 is a factor of 18. So 9 is one common factor in this expression. Let's look for some other common factors. Here I have a's in both terms. This is an a to the third power, so I have 3 a's over here. Here's an a to the second power, I have 2 a's over here. So the number of a's that are in common to both terms is just the 2 a's. Okay, I have 2 a's over here and I have 3 a's over here, but I need the a's that are common to both. So I have 2 in both. And I have an extra 1 over here. So a squared, or a to the second power, is also a common factor. Let's look at the b's. This is b to the fourth power and this is b to the third power. Okay, I have 4 b's over here and I have 3 b's over here. So the common factor among these two terms is the 3 b's. I have 3 over here and 3 over here. I also have an extra b over here, but that extra one isn't common to this guy. So my common factor for the b's is b to the third power. What I've done here is listed each of the individual common factors, and when we put them together, when we multiply them together as factors, we get what's called the greatest common factor, abbreviated the GCF. And the greatest common factor is something that you will need to find in order to factor an expression. In order to factor this expression, I'm going to take this GCF, I'm going to take the greatest common factor, and I'm going to pull it out of the expression. I'm going to pull out these factors by dividing this greatest common factor, dividing it out of each term that I have here. Now this will divide evenly because of the way that I've written down this greatest common factor. Just by nature of this being a common factor, it will divide evenly into each term. So let's see what I mean. I'm going to write down this GCF. I'm just going to rewrite it right here. 9a to the second power, b to the third power. And then I'm going to take this greatest common factor and I'm going to divide it out from this first term. So 9a to the third power, b to the fourth power, divided by 9a to the second power, b to the third power. Well, let's see, the 9's will cancel, right? 9 divided by 9 is just 1. So there's no constant term left anymore. A to the third power divided by a to the second power. Okay, I have a to the third over a to the second. Remember, when we divide these types of exponential terms here, we subtract the exponents. So 3 minus 2, I have 1a left over. 1a. I'm going to write him right here. All right, then I have b to the fourth power. I'm going to divide that by b to the third power. 4 minus 3, I have 4 b's. I'm dividing out 3 of them. I'm left with 1 b. 4 minus 3 is 1. I'm going to write this b right here. So when I pull my greatest common factor out of the first term, I write here in parentheses what's left over. I have one a left over and one b left over. We're going to do that same thing with the second term and add it together because I have addition right here. So I'm going to write down this plus sign. Now I'm going to take this second term and divide it by, once again, my GCF. So 18 divided by 9, that gives me 2. A to the second power divided by a to the second power, well, that's just 1, right? All of my a's are divided out. B to the third power divided by b to the third power, that is also 1. All of those b's get divided out. So for my second term, I'm just left with 2. The result here is a factored form of our original expression. We have the GCF out front, and we have the leftovers here added together in parentheses. And you'll notice that now we've written this expression that had a big old plus sign in the middle. We've written it in terms of multiplication. Now we have one factor, the greatest common factor, and we have another factor. This whole piece in parentheses, even though it has an operator in it, is a factor as well. So we've written our expression in terms of these two factors. We have successfully factored the expression. Let's have a look at our second example. Here we have, once again, two terms, and each term here has factors. Here x squared is a factor, x plus 2 is a factor of this multiplication, and here 3 is a factor and x plus 2 is a factor of this multiplication in this term. So to find the greatest common factor of the entire expression, I want to look for a factor or factors that are common to both terms. X squared, x to the second power, and 3, they don't really have anything in common. But x plus 2 and x plus 2, this factor appears in both terms, so it is a common factor. Now there aren't any other things that appear in both terms, no other factors that appear in both places, so x plus 2 is my greatest common factor. I'm going to take this greatest common factor and write it out front. Okay, this is going to be my first factor in my factored expression. Now I'm going to take this x plus 2 and I'm going to factor it out of each term by dividing. So let's look at the first term. X squared, x plus 2. If I divide this by x plus 2, well, the x plus 2 on the top and bottom will cancel each other out, and we're left over with x squared. Let's do this as well to the second term. Let's find those leftovers in the second term. So I'm going to use addition here because I have addition up here. I'm going to take 3x plus 2 and divide it by x plus 2. The x plus 2's on the top and bottom will cancel, and I'll be left with just 3. So here's my greatest common factor. Here's the leftovers from the first term and the leftovers from the second term. Together, these leftovers make up the second factor in my factored expression. These first two examples describe the basis of the process of factoring. This third example here involves something a little bit more complicated. If you look at this whole expression here, 3x to the third plus 9x to the second plus x plus 3, I don't have any factor that's common to all four terms. I don't have an x in each one, I don't have a 3 in this one, I don't have one factor that's common to all four terms. However, the first two terms have some things in common, and well, these next terms, I don't know, they've kind of got some related things as well, but yeah, they're just kind of hanging out over here. This type of example introduces the idea that we can factor by grouping our terms. So we can consider the terms of our original expression in groups and factor those groups individually as our first step, and then continue to factor the entire expression as our second step. So I've written this bracket in here. First, I'm going to consider just these first two terms. I'm going to factor these first two terms. So the greatest common factor of just these two terms, let's see if we can figure it out. We have a 3 here and a 9 here. The common factor of 3 and 9 is 3. I have an x to the third here and an x to the second power. The common number of x's is 2 x's, x to the second power. So I have 3x squared as the greatest common factor of these first two terms. I'm going to write that greatest common factor right here. Now, just like in the first two examples, I'm going to divide each term by the greatest common factor and write the leftovers with their addition operator in parentheses. So 3x to the third power divided by 3x to the second power just leaves us with 1x left over. I'll write that x here. 9x to the second power divided by 3x to the second power. Well, those x's to the second power will cancel out, and the 9 divided by 3 will give us a 3 left over here. So these first two terms get factored into this expression right here with these two factors. Now let's have a look at the second two terms, x and 3. Now, they don't have any common factors going on here that are greater than 1. 1, obviously, is a common factor of everything. You can divide anything by 1. So I do want to factor this. I want to factor x plus 3, but I don't have anything else in common other than the number 1. So let's try to pull out a number 1. My greatest common factor here is the number 1. So I'm going to write down a 1 here. And then I'm going to divide each term by 1 and see what's left. X divided by 1 is x. 3 divided by 1 is 3. So my greatest common factor is 1, and my leftovers, well, is everything that's already here, but they're my leftovers from pulling out my greatest common factor. Now both of these groups are being added together here, so I have them added together in my first factoring step. And what you'll see here is that if you look at all of this together, I've now created a new version of the expression. Okay, it's equivalent, but it looks different. Now I want to look at this version and look for common factors between the terms here. I've taken these 4 terms and I've made them look like 2 terms added together. And I want to see if there's any common factor between the 2 terms. 3x squared doesn't seem to have anything in common here, but x plus 3, he has a match, x plus 3 over here. So x plus 3 is a factor in both of my terms. So he's the greatest common factor in both of these terms. I can pull out the x plus 3, write it here, and then divide each of these big terms by that greatest common factor and write my leftovers in parentheses. So 3x squared times x plus 3 divided by x plus 3. Well, those x plus 3's will go away, and 3x squared is a leftover. We'll write him here. We'll write down our addition and then do the second term. 1x plus 3 divided by x plus 3. The x plus 3's will cancel once again, and we're left with 1. So what I've done here is I've created these 2 factors, x plus 3 times 3x squared plus 1. Now that we have our entire expression written in terms of things that are multiplied together, we are finished factoring for this example. So here's our original expression, 9x to the power of 4 plus 6x minus 27x to the third minus 18. The first thing we want to do, of course, is to look to see if there is any common factor among all of the terms. So here, there doesn't look to be too much in common because I don't have an x in this last term. So I know I don't have any common factors of x, but 9, 6, 27, and 18, they all have a common factor of 3. So 3 is the greatest common factor of all of these terms together. I'm going to pull out that 3, and then in parentheses, I'm going to write down the result when I divide each term above by the greatest common factor of 3. So 9x to the 4th divided by 3 gives me 3x to the 4th. 6x divided by 3 is 2x. Negative 27x to the 3rd divided by 3 is negative 9x to the 3, and negative 18 divided by 3 will give me negative 6. The result here is I have a factor outside the 3, and inside here I have an expression that no longer has a common factor for all of its terms, but I do have common factors among groups of terms. So I'm going to leave this 3 and these big parentheses hanging out here. I'm not going to be concerned with them for now. For now, I'm just going to proceed factoring the groups on the inside of these parentheses the same way we did in the previous example. So let's look at this group of terms here, 3x to the 4th plus 2x. My greatest common factor, let's see, 3 and 2 don't have a common factor, but x to the 4th and x, well, there's an x in common in both of these terms. So the greatest common factor for these two terms is x. I'm going to pull him out right here. Again, I'm just leaving this 3 in the parentheses written out here, but I'm not going to change anything about that at this point in time. So I'm pulling out this greatest common factor of x, and then I'm going to divide each of these two terms by the x and write what remains in here in parentheses. 3x to the 4th power divided by x is 3x to the 3rd, and 2x divided by x is just 2. So I have factored my first group of terms, and the result is here. I'm going to factor my second group of terms the same way, negative 9 to the 3rd minus 6. It looks like my greatest common factor is just a number that divides into both 9 and 6, negative 9 and negative 6 to be specific. That would be negative 3. So I'm going to pull out a negative 3 and then write down what remains when I divide both terms by that negative 3. Negative 9x to the 3rd divided by negative 3 leaves me with a positive 3x to the 3rd. Negative 6 divided by negative 3 gives me a positive 2. So this is my factored form of my second group of terms. Now I want to look at just these two terms, really, that I have on the inside of the parentheses here. It looks like I have another common factor among these two terms, and this factor is very fancy looking. 3x to the 3rd plus 2, 3x to the 3rd plus 2. That 3x to the 3rd plus 2 is a common factor to each of these terms. So I can pull that common factor out, 3x to the 3rd plus 2, again just leaving my 3 in parentheses where they are. And I'm going to divide each term, this one and this one, by that 3x to the 3rd plus 2. So x, 3x to the 3rd plus 2, divided by 3x to the 3rd plus 2. This big stuff cancels out, leaving just x as a leftover. And negative 3, 3x to the 3rd plus 2, divided by 3x to the 3rd plus 2, leaves me with just this negative 3 left over. Now I have a 3 on the outside, and I have two completely factored terms here on the inside. Since everything is just multiplied by everything else, okay, I don't have any addition existing outside of my factored terms, okay? I have addition and subtraction within factors, but I don't have any addition or subtraction outside of those factors. I just have this 3 multiplied by this big factor multiplied by this big factor. I can just remove this extra set of parentheses, and the meaning of the expression will stay the same. So my final factored result is 3 times the factor 3x to the 3rd plus 2 times the factor x minus 3. So in this first page of notes, we have successfully factored a variety of polynomials by pulling out common factors and by grouping. In the pages of notes so far, we've looked at factoring polynomials that had 4 terms by grouping, and we factored polynomials that had 2 terms by pulling out common factors. In this next page of notes, we're going to look at factoring a very specific type of polynomial called a quadratic. These are second-degree polynomials, and there are some special techniques that apply to factoring quadratics. So the first example that you see here, we have a polynomial, it's a quadratic, 4x to the power of 2 minus 5x minus 6. Now, in order to factor this, I want to look first to see if there's any common factors among the 3 terms, and in this case there aren't. And if you're kind of stuck in that boat, here is the technique that you want to employ. We want to factor these 3 terms, so what I'm going to do is I'm going to break apart this middle term into 2 terms so that I have 4 terms that I can try to factor by grouping moving forward. So in order to take this negative 5x and to break it apart into 2 different terms without changing the meaning of this term, I'm going to ask myself 2 questions. What pair of numbers multiplies to negative 24 and adds to negative 5? Okay, where did I get those numbers from? The 24 comes from this last term and the first term. Okay, so if you take the coefficient on the highest degree term and the constant term and you multiply them, you're going to get this number. In this case, it's negative 24. I want to know what pair of numbers multiplies to negative 24, but also adds to negative 5. I guess that's one question with 2 parts. I apologize. But let's try to list some pairs of numbers that might do this for us. I'm going to start by listing pairs of numbers that multiply to negative 24. I have 1 and 24. If I put a negative on either one of them, it'll multiply to negative 24, but there's no way I can add or subtract 1 and 24 and get negative 5, so that pair won't work. How about 2 and 12? 2 times 12, if I put a negative on either one of those, will give me negative 24. But 2 and 12, I can't add or subtract them to get negative 5. Let's look at another pair of factors of negative 24. How about 3 and 8? 3 and 8, if I put a negative on one of these, I will get negative 24. Now 3 and 8, I want to make sure that these add up to negative 5. If I had the negative on the 3, well then I would get positive 5. I want a negative 5, so I'm going to leave this negative on the 8 because 3 minus 8, or 3 plus negative 8, is equal to negative 5. And 3 times negative 8 equals negative 24, the way that we want it. So I found my pair of numbers that accomplish this, 3 and negative 8. What I'm going to do is I'm going to take these numbers and use them to replace this middle term. Notice that negative 5x is made up of a 3x and an 8x, or it can be made up of these two terms. It can be written in this way because 3x minus 8x is equal to negative 5x. So there's nothing stopping me from replacing the negative 5x in my polynomial with this new version of negative 5x, 3x minus 8x. So I'm going to do that. I'm going to take this polynomial, and instead of writing the negative 5x in here, I'm going to replace it with 3x and negative 8x. Because 3x minus 8x equals negative 5x, this piece in the middle, these 2 terms, are equivalent to this one term that we've replaced. So here is my new rewritten polynomial. In the next line below, I've actually written the same thing, I've just swapped the middle 2 terms. The reason I've done this is just to show you that it doesn't matter which order you put your pair of numbers in when you replace the middle term of your polynomial. You can write it this way, or you can write it this way. It will make the next step look a little bit different, but no matter what order you put these 2 terms in, your answer, your result, your factored result will turn out the same. So let's have a look at this one right here. 4x squared minus 8x plus 3x minus 6. I'm going to look at this now with these 4 terms in 2 groups of 2 terms. Here's my first group of terms, 4x squared minus 8x. Do they have a greatest common factor? And they do. 4 and 8 have a common factor of 4, and x squared and x have a common factor of x. So 4x is my greatest common factor, and when I divide 4x from the first term, I'm left with x. When I divide 4x from the second term, I'm left with negative 2. For the second group, 3x minus 6, let's see if there's a greatest common factor. 3 and negative 6 have a common factor of 3, and there's only an x in this one term, so it looks like my greatest common factor is in fact 3. Now let's see, if I divide my first term by 3, I'm left with x. If I divide my second term by 3, I'm left with negative 2. Now in this new expression here, you'll notice that we have two big terms, and those two terms share a common factor of x minus 2. So I'm going to pull out that common factor of x minus 2, write it here, and then divide the first term by x minus 2, I'm left with 4x. Divide the second term by x minus 2, and I'm left with 3. My result here is my completely factored version of our original quadratic polynomial. There are many methods you can use to factor quadratics, and you may remember some of them from former math classes in high school. These methods depend on whether your first coefficient, your leading coefficient is 1, or whether it's a different number. You also may have recognized specific types of quadratics, such as the difference of squares or perfect square trinomials, things of that nature. Those all have very specific ways that you can factor them. But this method of factoring quadratics that I've demonstrated in the first example here is my favorite, and it's because this method of factoring will work on any quadratic that is factorable by hand. So you don't have to kind of decide what kind of quadratic you have and then apply one of 7 different rules that you've memorized. You can just use this same method of finding a pair of numbers that multiply to something and add to something else, and then factor by grouping. You can use this method for absolutely any quadratic polynomial that can be factored by hand. So to get a little bit more practice with maybe a more complicated looking version of this, I want you to have a look at this second example, 18x to the third minus 141x squared minus 24x. Now, the first thing I want to do is, of course, look at all of the terms and see if there's a common factor among all of them. In our first example, there wasn't a common factor right off the bat, but here it looks like there might be. We have an x in each and every term, and we have 18, 141, and 24. I think not only do we have an x common to every term, but 3 divides evenly into 18, 141, and 24. So I'm going to pull a factor of 3x, a greatest common factor of 3x, out of each term. I'm going to write that greatest common factor here, 3x. Now I'm going to divide each term by that 3x. 18 divided by x to the third divided by 3x leaves me with 6x squared. Negative 141x squared divided by 3x is negative 47x. And negative 24x divided by 3x leaves me with negative 8. Now, this expression that I've created, this equivalent expression, you'll notice I have a factor on the outside, this 3x in the parentheses. We're going to basically ignore that for the next several steps of factoring our expression. In the parentheses, I have a quadratic. This is a second-degree polynomial. And there are no more common factors to each of these 3 terms, so I can move on to the method we employed in the last example. I'm going to look at the leading coefficient, and I'm going to look at the constant term. I'm going to multiply them. That is negative 48. Then I'm going to have a look at this middle term, the first degree term. The coefficient there is negative 47. I'm going to ask myself, what pair of numbers multiply to negative 48 and add to negative 47? Well, those are big numbers that might look a little bit scary to you, but since we need them to add to just one number off from 48, I think that the factors 1 and 48 might do the trick. If I make the 48 negative, 1 times negative 48 is negative 48, and 1 plus negative 48, or 1 minus 48, is negative 47. Here's my pair of numbers that accomplish this multiplication and addition property. This means I can take this pair of numbers and I can use it to substitute this negative 47x. I can break this term apart using 1 and negative 48 without changing the meaning of the expression. So let's do that. I'm going to rewrite this expression, except instead of writing negative 47x, I'm going to write positive x minus 48x. Here there's a coefficient of 1 here. Here's my 1, and here's my negative 48. Again, it doesn't matter what order you put these in, as long as your negative is attached to your 48 and you have your positive 1. So I've replaced negative 47x with positive x, positive 1x, minus 48x. And here is the rest of my expression listed exactly the same as it is above, with that one replacement made. Now, again, ignoring this 3x and the big parentheses outside, I'm going to look at the 4 terms that I have on the inside. I don't have any common factors among all 4 terms, so I'm going to break this apart into 2 groups of 2 terms and factor each group separately. So here's my first group, 6x squared plus x. My greatest common factor between these 2 terms is just the x. So I'm going to pull out my greatest common factor and divide each term by that greatest common factor. So 6x squared divided by x is just 6x, and x divided by x is 1. I'm going to do the same thing here with my second group of terms, negative 48x minus 8. The common factor I have there is that number 8, negative 8 in fact, so I will pull out a negative 8. And then I will divide each term by that negative 8. Negative 48x divided by negative 8 is a positive 6x, and negative 8 divided by negative 8 is just a positive 1. So I have inside these big parentheses here, I have a new factored version of the expression above, and I've created 2 terms out of the 4 terms. And among these 2 terms, I can see another common factor. This 6x plus 1 is appearing in both of these 2 terms. So I can pull out that common factor as well. I'm going to write it here. Again, just keeping the 3x on the outside. We won't touch that yet. 6x plus 1 is my common factor. I'm going to divide this whole first term by 6x plus 1, and I have x left over. I'm going to divide this whole term, negative 8 times 6x plus 1 by 6x plus 1. The 6x plus 1s will cancel out, and I'm left with a negative 8 left over. Now you can see I have the 3x out front multiplied by the 6x plus 1 multiplied by x minus 8. All 3 of these things are just multiplied together. I have some addition and subtraction, but they are within multiplied factors. So this 3x, he's just multiplied along with everything else, and I have no further need for these big parentheses. So I can write my final factored result as 3x times 6x plus 1 times x minus 8. Now there's no more common factors that I can pull out of each term. I am finally done factoring. I've created some more examples for us to have a look at because even though this is the one method that works for every factorable quadratic, sometimes our quadratics will look a little bit different than the ones that we saw in the first example, and I don't want you to get stumped by things that might look a little bit different. So this first example here, x squared plus 8x plus 16, that looks pretty straightforward. Let's first check to see if there's any common factors among the 3 terms, and it does not look like there are. So we're going to go ahead and employ our method. We're going to think about 2 numbers that multiply to this product, 1 times 16, multiply to 16, and add to this middle coefficient, 8. So 2 numbers that multiply to 16 and add to 8. How about 4 and 4? 4 times 4 is 16, and 4 plus 4 is 8. That seems to work. So I can take this 8x and replace it with 4x plus 4x, because after all, 4x plus 4x equals 8x. We haven't actually changed the meaning of the expression by doing this. Now we have 4 terms in a polynomial, and we can We can factor these four terms by grouping. So let's have a look at the first two terms, x squared plus 4x. Our common factor here is just going to be x. If I pull out an x and divide each term by x, I'm left with x from the first term and 4 from the second term. For our second group, sorry, this is a plus sign in case this little typo is bothering you, 4x plus 16. A common factor between 4x and 16 is 4. I'm going to pull out that common factor here and then divide each of these two terms by it. So 4x divided by 4 is x and 16 divided by 4 is 4. Now I have two bigger, fancier looking terms, and they do have a common factor among them. X plus 4 appears in both places, so I can factor out the common factor, x plus 4. And what I'm left with, when I divide this term by the x plus 4, I'm left with just the x. I'll write him here. And when I divide this term by the x plus 4, I'm left with just 4. I will write that here. Oh, interesting. In this example, we're left with x plus 4 times x plus 4. This is one of those special types of quadratics that you may remember from previous math classes called a perfect square trinomial. Okay, there's quadratics of this form that work out this way. They're known as perfect square trinomials, and when you do a lot of factoring of quadratics, you may come to recognize the perfect square trinomial before you factor, and in that case, well, you can kind of skip ahead and rush through if you know that it's going to turn out with two of the same factor. But for this class, that isn't necessary. Just employ this one method. It will always work for you every time. Let's have a look at another quadratic that looks a little bit fancy but can be solved by our same method. This is x squared minus 9. Some of you might recognize this as a difference of squares. If you do, you might be able to skip ahead by taking the square root of 9 and knowing that your result is going to be x plus 3 and x minus 3. If you don't see it that way, that is completely fine because this is just another quadratic that we can apply our same method to factor. So what makes this one different is we only have two terms and we're missing what's called the middle term. Well, it's not called the middle term, I call it that. It's the first degree term. We don't have a term with just an x. We have an x squared term and we have a constant term, but our just x term, which should be in the middle, is missing. The reason it's missing is because its coefficient is 0. So there's no reason to write it there if it has a coefficient of 0. So if you'd like, you can actually rewrite this, if it makes you feel better, as x squared plus 0x minus 9. Okay, that might help you move along. So we don't have any common factor among these two terms, so let's go ahead and try our method. We're going to multiply the leading coefficient by the constant term. 1 times negative 9 is negative 9. And we want to find two numbers that multiply to negative 9 and add to our missing middle term coefficient, which is 0. So we're looking for two numbers that multiply to negative 9 and add to 0. Well, if these two numbers are going to add to 0, they have to be the same number, one positive and one negative. That tells me we're looking for the square root of negative 9, right? You can go through and try out all your factors. That's just a little something you can notice to take a little bit of a shortcut here. So the square root of 9 is 3. That might be a good place to start. Let's see if the 3's work. If I multiply 3 by negative 3, I get negative 9. And if I add 3 and negative 3, I get 0. Aha, that works. Okay, so 3x minus 3x is equal to 0, and that's exactly what our middle first degree term is. It's not even there, okay, so it's 0. So I can replace this invisible first degree term with my new set of terms, 3x minus 3x. I've written that out for you here. X squared plus 3x minus 3x minus 9. Okay, this actually is the same as what's up here, because notice we just added two things into here, but these two things essentially equal 0, so we haven't changed the meaning of the expression. Now that I have my four terms, I can factor this by grouping in the usual way, so let's look at the first group, x squared plus 3x. I'm going to pull out the common factor, which is x, and divide each term by x. X squared divided by x leaves 1x left over. 3x divided by x leaves the 3 left over. Here's our next two terms. Negative 3x minus 9. The common factor between them will be negative 3. I'll pull out the negative 3 and divide each term by it. Negative 3x divided by negative 3 leaves an x. Negative 9 divided by negative 3 leaves me with 3. Now here you see I have in parentheses a common factor among my two terms, x plus 3. I'll pull out that x plus 3. And what I'm left with when I divide the first term, when I divide this term by x plus 3, I'm left with this x. I'll write him here. When I divide this term by x plus 3, I'm left with this negative 3. I will write him here. Okay, so this turns out to be x plus 3 and x minus 3. There's no coincidence that the 3's, which are the square root of 9, are down here, and we have the positive and negative, which results in that middle term canceling to 0 and that last term being negative. So this is the fancy difference of squares type of quadratic, but again, you don't need to know that. If that's something you already know, you're welcome to use a difference of squares technique. If not, you can always just follow this method and result in this very nice looking factored solution. For our final example, we have something that looks even more different, okay? I've made it look extra different by replacing my x with a t, just to be fancy. Some of your assignment questions and test questions will have different variables other than x in them, so I don't want that to throw you for a loop. This one has another difference. Not only is it a t instead of an x, but it is missing its middle term, its first degree term as well, just like the example before it. And there is even one more difference, and that is that the degree of this polynomial is 4, not 2. So what is it doing in the quadratic section? Well, it's here because we can employ the same technique we use for quadratics on this 4th degree polynomial because it's a special one, and you'll see why. The first thing I want to do, of course, is look for a common factor among these two terms, and I believe there is one. 25 divides into 15,625. You can check that with a calculator if you need to. So let's pull out the common factor of 25. When I divide each term by 25, I'm left with a t4 from the first term and negative 625 from the second term. After this is when something interesting is going to need to happen. In order for us to employ our method for quadratic polynomials, I'm going to need to have something to degree 2, not to degree 4. But something to the power of 4, to an exponent 4, is kind of related to an exponent of 2 because if you'll remember back to raising exponents to exponents, we can rewrite the exponent 4 as t to the second raised to the second. So if we raise the second power to the second power again, that is the same as t to the 2 times 2, also known as t to the 4th power. So I'm going to consider my variable. Instead of my variable being t, I'm going to think of my variable as if it's t squared. Because if I take t squared and I square it, well, that's a nice looking, second degree term. I can think of it that way. So I'm going to rewrite this so that I have a nice friendly second exponent equal to 2 here instead of an exponent equal to 4. I've rewritten this here, so I have 25 on the outside. My t to the 4th power is replaced by t to the second raised to the second, and I've just written my negative 625 here. Now, I can employ my same method. I'm going to multiply my constant term, negative 625, by my highest degree term, coefficient. Notice there is no coefficient out here, okay, where I'm pointing. You don't want to use the 25 here because we've already pulled him off. We've already factored him out, so he is no longer the coefficient on our t variable term here. So I have negative 625 times 1 I'm going to find numbers that multiply to that, negative 625. And remember, I'm missing that middle degree term, so that coefficient is considered to be 0. So two numbers that multiply to negative 625 and add to 0. Well, if they're going to add to 0, they have to be the same number, right? One positive and one negative. So I'm going to take the square root of 625 and see if that works. And it does. Square root of 625 is 25. So if I take 25 and negative 25, if I multiply those, I get negative 625. And when I add them, of course, I get 0. So if I were to take this 25 and put it as a coefficient on a t squared term, as well as do the same thing with my negative 25, if I add these terms together, I'm going to get 0. So if I put this new little expression that I've created in the middle of my polynomial here, it's not actually going to change the meaning of the expression. It's just going to make it possible for me to factor by grouping. So in this next line here, I've done just that. I've taken exactly what's written here, except in the middle, between the t squared squared and the 625, I have written in 25t squared minus 25t squared. What you'll notice is I have the 25 hanging out front, and on the inside of these parentheses, I now have 4 terms that I can. So let's have a look at the first group here, t squared squared plus 25t squared. The common factor between these two is t squared. When I divide t squared squared by t squared, I'm left with t squared. And when I divide 25t squared by t squared, I'm left with just the 25. Let's have a look at the second group, negative 25t squared minus 625. The common factor here is negative 25. I'm going to pull out my negative 25 and divide the first term by it, resulting in just t squared. Dividing the second term by it, I'm going to be left with a positive 25. So I now have, with my 25 still hanging out front, I haven't touched him yet, I have on the inside of the big parentheses here, I have a new 2-term polynomial expression. And among these 2 terms, I have a common factor, t squared plus 25. I'm going to pull out that t squared plus 25 and divide each of the 2 terms by it. When I divide this first term by it, I'm left with just the t squared. I'll write him here. And then when I divide this second term by it, I'm left with just the negative 25. I will write that there. So now I have our final phrase here, our final expression. It has 3 terms, 3 factors multiplied together, and it is 25 times t squared plus 25 times t squared minus 25. We have successfully factored actually a 4th degree polynomial by writing him in terms of a 2nd degree polynomial and using our factoring method for quadratics. This brings us to our final page of notes for the first video portion of Unit 2, and that is when we take our factoring of quadratics and we make some use of all of that knowledge. In this page of notes, we're going to use our knowledge of factoring quadratics in order to solve quadratic equations. So up until now, we've just looked at quadratic polynomials. There were no equal signs in the original expression, but now we're going to look at quadratic equations. So quadratic equations are 2nd degree polynomials that are in standard form and set equal to 0. That's the equation part. So this first example of a quadratic equation is x squared plus 9x equals 0. Okay, we are asked to solve this for x, and the way that we solve a quadratic for x is by factoring and then doing some clever things with this equals 0. So I'm going to look at the left-hand side of the equation. I'm going to make sure that it's in standard form, meaning that it is listed in order of its degree for each term. So I have my highest degree term first and my second highest degree term second. That is good, we're in standard form. I'm also going to make sure that it's already set equal to 0, that I don't have to do any moving around of terms before I can get started. Once I verify that my equation is in this form, I can take the left-hand side and I can factor it. So x squared plus 9x has common factor, just one common factor of x. So I'm going to pull out that common factor and divide each term by x. X squared divided by x leaves me x, and 9x divided by x leaves me with 9. So here on the left-hand side is my factored form, and on the right-hand side is 0. Now, I want to solve this for x. I want to know what x actually equals. Now, there's a funny thing going on here. I have two factors multiplied together, x times x plus 9. And I know that when I multiply these two things, I get 0. Now, what do you multiply to get 0? Well, anything times 0 is 0, and 0 times itself is 0. But there are no two numbers on the planet that when I multiply them together, if neither one of them is 0, that will give me 0 when I multiply them. So think of numbers that aren't 0. If you multiply any two numbers that aren't 0, you're never going to get 0. So the idea here is that one of these terms, either the x or the x plus 9, or both, I suppose, have to equal 0 in order for this side of the equation to multiply to equal 0. Okay, that's the big concept that makes this method of solving quadratic equations work. So when I look at this, I know that either x equals 0 and or x plus 9 equals 0. If x equals 0, well, that's one solution, x equals 0. If x plus 9 equals 0, what value of x gives you this equation, fulfills this equation? Well, it's negative 9. You can find that by getting the x by itself, so subtracting 9 from both sides of this little equation here, and you'll find that x equals negative 9. So when x equals 0, this whole equation is 0, and or when x equals negative 9, this whole equation is 0. And you can test that out by taking these values of x and plugging them back in to make sure that you do in fact get 0. This fancy idea that we just discussed about these factors multiplying to equal 0 and what that means for the solution, it has a fancy name called the zero product property. So if you hear someone talking about the zero product property, they just mean that if you have two things multiplied together and they equal 0, it means that one of those things, at least one of those things, has to be equal to 0 itself. So let's apply this idea to another quadratic and see if we can use everything we've learned so far to solve this next quadratic equation. Here we have x squared minus 12x is equal to negative 36. Now remember, one of the first things I need to do is to make sure that my equation is in standard form and set equal to 0, and this one is not set equal to 0 yet. So what I need to do is I need to take this negative 36 over here and move them over to the left-hand side. So x squared minus 12x, I'm going to add 36 to both sides so that I have x squared minus 12x plus 36 is equal to 0. Okay, and this is good. This is in standard form because I have my highest degree term, my second highest, and my constant term, and I'm set equal to 0. Perfect. So now I can look at this left-hand side of the equation and factor it according to the things we learned in the last few pages of notes. I'm going to take my leading coefficient and my constant term and multiply them. 36 times 1 is 36. I'm going to look for a number that multiplies to 36 and adds to this middle term coefficient, negative 12. So two numbers that multiply to 36 and add to negative 12, I think that 9 and 4 will work. Now 9 times 4 is 36, and that's great, but that doesn't give me a negative 12. So I better make this 9 and this 4 negative, okay? Negative 9 times negative 4 is positive 36 because the negatives will cancel each other out, but negative 9 plus negative 4 is going to equal negative 12, which is exactly what I want. So I can take these numbers and I can use them to substitute my negative 12x. negative 12x here in my middle term can be rewritten as negative 9x and negative 4x. Again, the order doesn't matter here. So I've plugged these guys in. I've rewritten my equation, replacing only the negative 12x with a negative 4x minus 9x, which is the same thing. And I have rewritten everything else here. Now I have created a polynomial on the left-hand side that has 4 terms that I am able to factor by grouping. So let's look at this first 2 terms, x squared minus 4x. The common factor is x. The leftovers are x minus 4 when I divide each of these terms by their common factor. Here in my second group, negative 9x plus 36, the common factor here is negative 9. If I divide the first term by negative 9, I'm left with x. If I divide the second term, I'm left with negative 4. Now I have 2 terms on the left-hand side, and they do share a common factor, x minus 4. I'm going to pull out the common factor, x minus 4, divide the first term by it, and I'm left with this x. I'll write him here. And I will divide the second term by my common factor, x minus 4, and I'm left with negative 9. I will write that here. So here you can see I have my left-hand side of the equation completely factored to x minus 4 times x minus 9. These are 2 things multiplied together to equal 0. Enter the zero product property, okay? So one of these factors has to be 0 in order for this to equal 0. So I know that either x minus 4 equals 0, or x minus 9 equals 0, or both. I'm going to figure out each one. For x minus 4 to equal 0, x has to be 4. For x minus 9 to equal 0, x has to be 9. So these are my 2 solutions to my quadratic equation. I should have noted that in the first example, that for these second-degree polynomials, it's okay to get 2 answers, right? 2 different x's will satisfy this equation, okay? And that's actually indicated by the degree of the polynomial that's in our equation. So our solution here is x equals 4 and x equals 9. Let's have a look at one more example here. This one looks very fancy. We've got all kinds of stuff going on. 14x squared plus 9x plus 2 is equal to 10x plus 6. Okay, this is not yet in the standard form, and it is not set equal to 0. So what I need to do to get it equal to 0 is I need to move the 10x and the 6 over to the other side. I will subtract 10x from both sides, and I will subtract 6 from both sides. That will cancel this stuff out on this side and give me 0. And what I'm left with on the left is 14x squared plus 9x minus 10x plus 2 minus 6. Okay, I've written this kind of in the order of the standard form in descending degree order. And I have here some common, I shouldn't say common here, I should say like terms, right? I have some like terms with my x's and my constant terms. So I have 9x minus 10x, I can move that together, I can add those. And 9 minus 10 is negative 1, that becomes a negative x. And 2 minus 6, that's negative 4. I will write that here. So I've rewritten this equation in a standard form and set equal to 0 and simplified. So I have 14x squared minus x minus 4 equals 0. Okay, now I can employ my method for factoring the left-hand side. Let's take 14 times negative 4. That is negative 56. I'm looking for 2 numbers that multiply to negative 56 and add to the coefficient on the middle term, which is negative 1. Multiply to negative 56 and add to negative 1. The factors that I think will do that are 7 and negative 8, right? 7 and 8, 7 times 8 is 56. I need to make one of them negative. Since I want them to add to negative 1, I better make the larger one, that 8, negative. 7 times negative 8 is negative 56, and 7 plus negative 8 is negative 1. This will work quite nicely. I can replace my negative x with 7x minus 8x. That is an equivalent form. So you can see here I've rewritten exactly this equation, except I've taken the negative x and I've replaced it with a positive 7x minus 8x. Now here is my new version with 4 terms that can be factored by grouping. Let's take the first 2 terms. Their common factor is 7x. 7x will come out here. 14x squared divided by 7x leaves me with 2x. 7x divided by 7x, well, that all cancels out to a plus 1. Here in my second group, I have negative 8x minus 4. The common factor is negative 4. Negative 8x divided by negative 4 is 2x. Negative 4 divided by negative 4 leaves me once again with a positive 1. Now I have 2 fancy looking terms that share a common factor, 2x plus 1. Let's pull out the 2x plus 1. And when we divide the first term by it, we're left with just a 7x. I'll write him here. When we divide the second term by it, we're left with just a negative 4. I'll write him here. So 2x plus 1 times 7x minus 4 is our completely factored version of this, this equation, or the polynomial that's in this equation on the left-hand side when we moved it over. So I have 2 factors multiplied together that equal 0. According to the zero product property, either this one, 2x plus 1 is 0, or this one, 7x minus 4 is 0, or both. So let's figure out either case. In this case, let's solve this little equation for 0. Let's get x by itself. I'll subtract 1 from both sides, and then I'll divide both sides by 2, and you will see that x is negative 1/2. On this side, I'm going to solve 7x minus 4 equals 0 for x. I'm going to add 4 to both sides and then divide both sides by 7, and the result will be x equals 4 over 7. So my solution here is that x is equal to negative 1/2 and x is equal to 4 over 7. Once again, we have 2 solutions to our quadratic equation.